Can you see my screen?
Yes.
So, I'm from University of Aveiro in Portugal. I would like to say thanks to organizer to invite me for this presentation. Is everything okay?
Yes, all is good. You can begin.
Okay. Today I would like to have a talk about the flexible electrodes that we prepare in our laboratory and use it for supercapacitor device. As you probably know, graphene and reduced graphene oxide is a carbon family based materials and can be widely used in our life, for example, for energy harvesting device, something like photovoltaic cell that we can convert solar energy to electrical energy, or for energy storage material, something like battery device. In my case, I want to say today about supercapacitor device. Supercapacitors is electrochemical capacitor, and the main parameter for this device is specific power. As you can see from this Regon plot, supercapacitor has a high power, but not so high energy in comparison to battery. And if we will compare simple capacitor and battery, we will see that supercapacitor belong between these two devices. In opposite to battery, supercapacitor has energy storage mechanism on interface between electrolyte and electrode. We can say that we have two different types of energy storage mechanism: electrostatic storage, and mainly it can be found in double layer capacitors, and pseudocapacitor device. In this case, we have some additional capacity that can be found on the top of the electrodes. And if we will see the main characteristic for this device, electric double layer capacitors can show almost rectangular shape for cyclic voltammetry. In case of pseudocapacitors, we have some additional pseudocapacity on the top of surface of electrode. But in case of battery, if you will see, we see this peak in a cyclic voltammogram that can be changed with increasing of potential. It means that here in battery we have incorporation of our charge inside in electrodes, but in case of supercapacitors we will see only on the between in the electrolyte and electrode, or sometimes on the top of electrode. So it is very important to understand that when we have materials belong to supercapacitors and materials when we can see battery type of energy storage. And the second parameter that is important for this characterization is charge-discharge curves. For supercapacitor, it should be triangular curve, but in case of battery, it's completely different. So back to our goal, battery can be used widely, but battery doesn't have high power density. In case of supercapacitor, device can show high density, but not so high energy density. And as I said before, graphene is widely used for energy storage device. Why graphene? Graphene is a very interesting material. It is one layer of carbon, and in theory, it's ideal material with high surface area, with high electrical conductivity, very nice mechanical properties, but it is very difficult to obtain. So monolayer can be prepared by chemical vapor deposition or molecular beam epitaxy, but it's not so easy. Moreover, we can prepare only small size of graphene. So typically in laboratory, we can prepare reduced graphene oxide. What it means? We have graphite, very cheap material and not difficult to prepare it. We can make a chemical treatment to obtain graphite oxide. After that, we can reduce the size of graphite oxide and we will have graphene oxide. And after chemical or thermal treatment, we can obtain reduced graphene oxide. So it's easy to prepare in laboratory, and if you will see in literature, the main part of research was done in on a reduced graphene oxide solution. So first of all, we think about preparation of supercapacitors without any binders. So we use reduced graphene oxide. First of all, we prepare a solution, graphene oxide, and also graphene oxide modified with polycarbonate. We use simple vacuum filtration, as you can see here. We obtain some disc. It can be different size. We prefer this one not so big. We want to keep material, and we make annealing thermal treatment to obtain reduced graphene oxide at 2 different temperatures to check the electrical properties. That is also important for preparation. So when we check by scanning electron microscopy, as you can see, sample obtained at the lower temperature, not different from sample obtained at higher temperature. But in case of incorporation of polycarbonate, the structure was dense. We check this material for supercapacitor. We decide to use very simple materials that can be found in each laboratory. We use PET substrate, simple plastic. We use copper tape, and we use two-side carbon tape. So we just cut it and glue it. And on the top, we press our sample, put separator together with electrolyte, and make face-to-face 2 electrodes. So it looked like that. Also, electrolyte was simple salt, nothing more. When we measure cycling voltammetry, as you can see here, the shape of all our sample was not so ideal like we expected for supercapacitors. So it means our device has high resistance. And as you can see, tape has glue, and we think this glue doesn't work properly for electrical conductivity. So when we check charge, discharge, charge, and discharge, also our device can show different behavior. And in result, when we calculate volume capacitance, the value was not so high as we expected, and not a lot of difference. So we understand that we have limitation, first of all, because of restacking of reduced graphene oxide layer. It means no good way for electrolyte inside in material. And second, tape is not good material because of a lot of resistance of glue. So, and we start to prepare another supercapacitors based on composites. For composite, we use reduced graphene oxide gel. For that, we prepare graphene oxide by freeze drying. It was porous structure, very light. We check it by also anneal at 2 different temperature. We check it by XRD, by Raman, and the XPS analysis. We found that with increasing of temperature, the quantity of oxygen decreased significantly. And we mix it with carbon nanotubes to use it like spacer between reduced graphene oxide layers to be sure that we have space for electrolyte. Use a PVDF polymer like binder and use carbon cloth as substrate to make flexible electrode, as you can see. We check it on by SEM, and as you can see, in case of aerogel annealed at lower temperature, we have more homogeneous slurry that can go through carbon cloth. But in case of higher temperature, it was probably not so wettable and not so homogeneous distribution. So we check single electrode also by CV cyclic voltammetry, and you can see here almost ideal rectangular behavior in both cases, lower temperature and higher temperature, increasing with increasing of potential range. So, and galvanostatic charge curves also show us triangular behavior. So it means that we have ideal electric double layer capacitors. We combine them in full capacitors to use sodium electrolyte, and total full device show us that we have about 50 farad per gram capacitance for very wide electrolyte window. When we check it with time, we use 10,000 cycles to charge and discharge, let's say more than 140 hours. And as you can see, it was almost stable, not a lot of losses. It means that our two device can be prepared easy, but in case when we use binder free on copper and carbon tape, and in case when we use different additives on carbon cloth, in both the case, electrodes with materials annealed at lower temperature shown us better properties. Moreover, when we use electrodes on carbon cloth with additives like carbon nanotubes as spacer, we can use our device long time without significant losses. So I would like stop on that and say thanks to my colleagues who helped me with these measurements, people from Finland and Italy who helped me with electrochemical characterization and with XPS analysis. Also, I would like to say thanks to Foundation from Portugal, Foundation Science and Technology, European Cost Action, and European Consortium Innovation University, who helped me with financial support for mobility grant in University of Tampere and Research Center in Italy. Also, again, I want to say thank you for organizer and thank to you and invite you to use this information for your future publications that we can support you to publish in nanomaterials with significant discount. Thank you very much for your attention.